All right, guys, the last little section that we have here is actually from Chapter 8. It's Section 8.7, and it's called L'Hopital's Rule. Okay, and it's actually back to relating to first chapter stuff when we were doing limits. So let's recall some limits problems of how to find the limit as we approach a certain value. And if I give you this problem, the limit as x approaches -1 of this function, the first thing that we always try to do anytime we do limits is do what? Okay. Direct substitution, right? So I would try to plug in my -1. -1 squared is 1. 1 times 2 is 2. 2 minus 2, I would get 0. If I plugged in a -1 on the bottom, -1 plus 1 is 0, right? And when we got 0 over 0, it doesn't mean that our limit doesn't exist. It means our limit actually does exist. We just have to figure out another way of doing it because direct substitution doesn't work. So what did we do if direct substitution didn't work? Well, we did a couple things. One of them was trying to factor our problem and simplify. So I can GCF out a 2, leaving me with an x squared minus 1 that I can also factor into an x minus 1 and an x plus 1. So on the top factors into a 2, into an x minus 1, and an x plus 1. The bottom is an x plus 1, and then I can go ahead and reduce off my x plus 1 from the top and the bottom, and then I can redo my limit as x approaches -1. If I plug in a -1, I get -1 minus 1, which is -2. -2 times 2, so my limit would be -4, right? So as my limit approaches -1, I end up approaching -4 on the line. Okay? So that's an example of one where we had to factor, simplify, and then redo our limit. What if I gave you a problem like this? Okay? If I try again to do my direct substitution and I plug in a 1, the square root of 1 is 1, 1 minus 1 is 0 on the top. On the bottom, 1 minus 1 is 0, I get 0 over 0, which doesn't mean my limit doesn't exist, just means I have to figure out another way of doing it. So what was the second way that we did limits if we can't factor? Do you remember rationalizing? Multiplying the top and the bottom by the opposite of the top, so multiplying the top and the bottom by rad x plus 1. Foiling it out, I have x, the square root of x times the square root of x is x, the square root of x times 1 is positive square root of x, -1 times x is negative square root of x, so those ended up canceling, right? -1 times 1, I have an x minus 1 on the top. On the bottom, I have this x minus 1. I'm not going to distribute it through, because what happens from the top and the bottom now? Doesn't the x minus 1s cancel? And so then I'm left with a 1 over square root of x plus 1 on the bottom, and then I can redo my limit as x approaches 1. As x approaches 1, my limit is 1 over 2. I get 1/2, right? So those happen to give me 0 over 0. I can either simplify by factoring or rationalizing, and then redo my limit. But what if I get a problem that looks like this? If I try my direct substitution and I plug in a 0, what's the cosine of 0? 1. So 1 minus 1 is 0. If I plug in a 0 on the bottom, I get 0 over 0. So the limit does exist. I just have to figure out how to do it. But this one looks kind of weird. It doesn't look like one that can be factored. It doesn't look like one that can be rationalized. So I get a little bit stuck, right? Well, we get a little bit stuck until now. Now we're going to learn a rule that will work anytime I get what's called an indeterminate form. 0 over 0, or infinity over infinity, okay? Or negative infinity over negative infinity, okay? As long as f and g are differentiable functions, then if I take the limit of f, if I do my direct substitution and I end up getting 0 on top, and I do my direct substitution on bottom, I get 0 on the bottom. That's what's called an indeterminate form. Or if I do my direct substitution and I get an infinity on top, and I get an infinity on the bottom, or negative infinity and negative infinity, right? So it doesn't matter if it's positive or negative. These are what's called indeterminate forms. If you end up doing direct substitution and you end up getting one of these scenarios, what you can end up doing, the limit then of these two things divided, is going to end up being the same thing as the limit of their derivatives divided. So what I can end up doing is taking the derivative of the top, taking the derivative of the bottom, and redoing my limit. And I should end up getting the right answer. Okay, so let's go back to that problem, right? This was the same problem that we attempted before, 1 minus cosine x over x squared. We tried our direct substitution, we ended up getting 0 over 0. Okay, so this is one of my indeterminate forms. L'Hopital's rule says that I should be able to take the derivative of the top. So what is the derivative of 1? 0. What's the derivative of negative cosine? Positive sine, correct? And what is the derivative of the bottom, x squared? 2x. And then I should be able to redo my limit as x approaches 0. If I plug in a 0, what's sine of 0? 0? What's 2 times 0? Uh-oh, I get 0 over 0 again. That doesn't mean that my limit doesn't exist. L'Hopital's rule says that I should be able to do again the derivative of the top over the derivative of the bottom and resubstitute. Some of you might have seen a little trick here though. What is sine x over x as we approach 0? Does it turn into a 1? So let's see if your guess works. Don't forget about the 2 there. But if I didn't notice that, I can do L'Hopital's rule again. The derivative of sine is cosine. The derivative of 2x is 2. And I should be able to redo my limit as x goes to 0. What is cosine at 0? 1. That's where I got my sine x over x, right? Turns into a 1. But don't forget about I have the 2 on the bottom. So I end up getting a limit of 1/2. Okay? You might have to do L'Hopital's rule a bunch of different times. But as long as you have 0 over 0 or infinity over infinity, you should be able to use it as much as you need to get down to one final answer. Okay? Let's try another one. If I do the limit as x approaches 0, let's try our direct substitution. If I plug in a 0 here, what is e to the 0? What is anything to the 0 power? Isn't it 1? 1 minus 1 is 0 over 0. My limit exists, but I have an indeterminate form. I don't know what the answer is, so let's do L'Hopital's. L'Hopital's rule says I can do the derivative of the top. The derivative of e to the 2x is e to the 2x times 2. The derivative of x is 1, and then I should be able to redo my direct substitution as x goes to 0. If I plug in a 0 here, e to the 0 is 1. 1 times 2 is 2, right? Not possible without L'Hopital's rule, right? We couldn't factor it, we couldn't really rationalize it, we'd be a little bit stuck. But now that we know L'Hopital's rule, we can use it anytime we get an indeterminate form. Let's do another one. If I plug in an infinity, what is the natural log of infinity? Remember a natural log graph kind of looks like a breadstick graph? And as I keep going to the right, I'm just going to keep getting bigger and bigger and bigger values, right? So I end up getting infinity over infinity, which is not 1. Okay, I've got to figure out what it actually is. Since I don't know what it is and I can't factor and I can't rationalize, let's use L'Hopital's rule. Derivative of natural log of x is 1 over x. The derivative of x is 1. So really this is the same thing, it's just a 1 over x. And then I can redo my direct substitution as x goes to infinity. If I plug in a really big number here, what is a 1 divided by a really big number? Then I end up converging to 0. All right. There's one more on this page, and then we'll do a few more. Okay. If I plug in a negative infinity squared is a positive infinity. If I plug in a negative infinity, I already have a negative in front of it, so those two negatives make a positive. Remember, e is just a number, 2.7 something, right? So 2 to the infinity power is just going to be another really big number. Infinity over infinity. That means I can use L'Hopital's rule, right? If I use L'Hopital's rule, I have 2x over e to the negative x times negative 1. I can redo my limit as x goes to negative infinity. And I get what? A negative infinity over... another negative infinity. Now what? Let's just do L'Hopital's again. 2 over e to the negative x times another negative. So the two negatives end up making a positive in front there, right? Redo my limit as x goes to negative infinity, and I get 2 over a really big number, right? What is 2 divided by a really big number? Just 0. Okay? All right, let's see if I can try to trick you. Let's try this one. What do we always do first? Let's try your direct substitution. If I do my direct substitution, 1 squared is 1, 1 plus 1 is, 2. 1 times 2 is 2, 2 plus 1 is 3. Whoa, wait a second, what's my limit? Isn't it just 2/3, right? What happens then if I didn't do my direct substitution and I just assumed that I could do L'Hopital's? Let's see what happens. If I try to do L'Hopital's rule and I get 2x over 2 and I try my direct substitution as x goes to 1, so I plug in a 1 here, I get 2 over 2, which is 1. Is that the same answer that I get doing it the original way, direct substitution? No. So L'Hopital's rule does not work if you can do direct substitution. L'Hopital's rule only works if your direct substitution gets you an indeterminate form, 0 over 0 or infinity over infinity. Okay? So please, please, please always do direct substitution first. Then if it doesn't work, then you can do L'Hopital's rule. Okay? So the answer for this one is 2/3, not 1. Okay? All right. So some other indeterminate forms is 0 times infinity. What is 0 times infinity? Is that 0? What is that? It's kind of weird, right? Or what is infinity minus infinity? Is that 0? Well, how big are those infinities? Is one bigger than the other infinity? Right? Kind of hard to tell. These are another form of indeterminate values. And so what we're going to try to do is we're going to try to convert them into fractions, to try to get them to look like this or like this, and then we can do L'Hopital's. Okay? So instead of doing a 0 times infinity, we're going to try to get it to look like a fraction, and then we do our L'Hopital's from the last couple of examples. So let's try some problems. So if I, again, try my direct substitution, and I plug in my infinity, I get e to the negative infinity, and if I do that, e to the negative infinity, could I just actually bring that down to the bottom and make it positive infinity, like a positive exponent? And then I have the square root of infinity. So the square root of a really big number, isn't that still just going to be a really big number? And then e to the really big number is still just going to be a really big number. I don't know how big, but still big, so we're still going to call it infinity. And infinity over infinity is not 1. Okay? It is not 1. It's one of our indeterminate forms. So what I can do is I can still try to find my limit by doing L'Hopital's. But I would need a top and a bottom. I would need to do the derivative of a top and a derivative of a bottom. So I need to make this into a top and a bottom. So can I just take this e to the negative x and move it down to the bottom? And then I can do L'Hopital's rule from there. I could do the derivative of my top, which is 1/2 x to the negative 1/2. I could do the derivative of the bottom, which is e to the x times 1. And then I can try my direct substitution. Let's probably take this x to the negative 1/2 and bring it down to the bottom with that too, because that looks funky having a triple layer fraction. I'm going to keep my 1 on the top. I'm going to bring my 2 down. I'm going to bring my x to the 1/2 down, and then I have my e to the x on the bottom. And let's do the limit still, redo the limit as x goes to positive infinity. On the top I have a 1. On the bottom I have 2 times the square root of infinity, which is infinity, times e to the infinity, which is infinity. So I have a 1 divided by a really big number, which is 0 again. All this work for a little baby 0, huh? All right, let's keep going. I want to do one more of these. If I plugged in a 0, let's see what happens at 0. The limit as we approach 0 of x is just 0. Times, if I do the limit of a natural log, remember your natural log graphs, remember they kind of look like this, they look like breadsticks. What's happening as we come from the right of 0? Where am I going? Isn't that a vertical asymptote and I'm going down toward negative infinity? But what is 0 times negative infinity? That's one of our indeterminate forms, right? So can we somehow make this into a fraction instead? So this is what I'm going to do. I'm going to try to somehow make this into a fraction. I'm going to take this natural log of x and keep him on the top. Can I bring this x down to the bottom and make his exponent like a negative 1? Can I like reverse it, what I did last time? So let's do our L'Hopital's. L'Hopital says the derivative of the top. The derivative of natural log is 1 over x. The derivative of x to the negative 1 is negative 1 x to the negative 2. All right, we don't have triple layer fractions, right? That kind of looks funky. So let's actually rewrite this, and we're going to say 1 over x, and instead of dividing by negative 1 over x squared, could we really take this 1 over x and multiply by x squared over 1, the reciprocal? So what ends up happening? Did I miss a negative there? There it is. I end up reducing my x's and I end up getting negative x, right? But I still have to do my limit as x approaches 0 from the right. So what is the limit as x approaches 0 from the right of negative x? Would you look at that? We get another 0. Okay? Please don't say when all else fails, let's just guess 0, because it's not always the case. It just happens to be so on a lot of these examples. Okay? So please do what you can to get your actual limit, not just guess and answer. There are 2 other examples that I have, but I'm going to go ahead and skip these. I've made these into pencasts last year, so I will put them up on my website if you'd like to listen to the last 2 examples. They will be separate pencasts. I think you should be able to do, though, the homework with what we've just done already. The homework for 8-7 is going to be on page 574, and it's numbers 11 through 37 odd. Okay? All right, guys, I'll see you later.